Welcome to the Unit 3 Part 3 video series. In this particular video, you will be able to learn how to determine the number of electron domains and bonding domains there are around any atom, whether it's a central atom or whether it's an exterior atom. The overall series, the learning objective will be for you to be able to predict any of the three-dimensional geometries for molecules using VSEPR theory. So it's important for us to start at the beginning and talk about what VSEPR theory is. So let me get rid of that and let me pull this down. VSEPR theory stands for valence shell electron pair repulsion theory. Valence shell electron pair repulsion theory, we call it VSEPR because if we just highlight the first letters of each, it spells out the word VSEPR. Okay, kind of looks like VSEPR, but it's actually VSEPR. As you go through this, valence shell electron pair repulsion theory is really a kind of a straightforward thing to understand. The idea here is that the electron pairs repel each other because they have similar charges. All electrons are negatively charged, and so because they're all negatively charged, they will all want to repel. Now these electron pairs then space themselves evenly out around the three-dimensional atoms that are found in molecules. So I will tell you that in order to be very good at determining geometry, you're going to want to be very good at drawing Lewis dot structures. So if you need to go back and review Lewis dot structures, please do. So let me put this up here. Okay, I'll get rid of this. And so if we take a look at just the Lewis symbol for argon, we actually started drawing these structures keeping in mind VSEPR theory. Okay, because when we draw electron pairs, we draw them like this, so that the electrons are spaced as far away from each other as possible. We don't draw them so that they're all shoved up at the top or all on one side. We draw them equally spaced out around the molecule, in this case the atom. So you'll look that we have them spaced around. Okay. We could also take this guy. Okay. Now this is a simple Lewis structure. This is ammonia, and if we look, we again drew this so that all the atoms here are evenly spaced around the central atom. Notice that here we have put these 90 degrees apart from each other. Now, don't worry about the fact that that's 90 degrees. Keep in mind that we're just trying to equally space the electron pairs as far away from each other as possible. Why don't we worry about the 90 degrees? Because we have to realize that this is a three-dimensional object that we are trying to represent in two-dimensional space. So what we should have is something like this, where we have a central atom, which in that case was nitrogen, and then we had 4 pairs of electrons around the outside of the atom, that central atom. And so notice that because it's a three-dimensional shape, the shape of this is not, the angle here is not 90 degrees. The angle here is actually more than 90 degrees. This is actually one of the most common shapes in all molecular geometry. It's called a tetrahedron, and it is so called. If I pull down this other picture here, you'll see this is the same setup. You have a central atom with 4 things coming off of it, and if you shade it in, you'll notice that it's kind of got this triangular base and then these triangular sides, and so it kind of looks like a triangular based pyramid. And so it turns out that the bond angle for this, the angle between the electrons, works out to be 109.5. But there's more on that later. Before we get into the particulars of these, we probably should get down some vocabulary. So the first thing that we probably want to do is we want to go over what a central atom is, and we want to go over what an exterior atom is. The central atom is the middle atom. The exterior atoms, in this case, are chlorine. They're the atoms that go around the outside. Okay. Now, electron domains are places around any atom. It doesn't have to be necessarily the exterior or the central. It can be either one. Electron domains are places where there are electrons. So here we have electrons here, 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 and here. Okay? And then bonding domains are places where you find bonds. So in this case, here, here, and here. So what does this look like? What we can do is we can abbreviate electron domain, ED, and we can abbreviate bonding domain, BD. And so what I can do is I can say, well, how many electron domains are there around nitrogen? And I can count electron domains. So there's 1, 2, 3, 4. So there are 4 electron domains around nitrogen. Nitrogen has 4 electron domains. How many of them are bonding domains? 1, 2, 3. There are 3 bonding domains. But now if we switch and we look at chlorine, chlorine has how many electron domains? 1, 2, 3, 4, right? 1, 2, 3, 4. I can change my color here, so I can go 1, 2, 3, 4. So there's still 4 electron domains, but only one of them, this one right here, is a bonding domain. Okay, and we can continue to do this for other examples. Here's water. So how many electron domains and bonding domains does water have? Okay, well, in terms of electron domains, oxygen has 4 electron domains. 1, 2, 3, 4. Bonding domains, it has 2. There's only 2 places with electrons around it. Hydrogen, because hydrogen is so special, hydrogen will only ever have 1 electron domain and 1 bonding domain. The next example would be the nitrate polyatomic ion. Notice here that the nitrate polyatomic ion is bracketed, so we need to make sure that that happens, and the charge is here. Okay, so how many electron domains does nitrate have? How many bonding domains? Well, let's look. Nitrogen has 1, 2, 3 electron domains. The double bond counts as 1 electron domain. And for bonding domains, the nitrogen again has 3. All of the electron domains are bonding. For the oxygen, there is 4 electron domains, and there are 1 bonding domains for these oxygens here. Now, for this oxygen, there's another oxygen. Now, in this case, there are 3 electron domains and only 1 bonding domains. Okay, well, now let's see if you can try it yourself. So what you can do right now is pause the video and see if you can determine how many electron domains and bonding domains there are around each atom in the molecule. Okay, so I assume you paused it, so I'm going to just go through this real quick. For carbon and oxygen, for carbon there's 2 electron domains and 2 bonding domains. 1, 2 electron domains, both of them are bonding. For oxygen, each of them are the same, so there are 3 electron domains and only 1 of them are bonding. Now, for sulfur hexafluoride, okay, sulfur hexafluoride, the sulfur has 6 and 6. Each fluorine has 4 and 1 bonding domain. Now for sulfur dioxide, sulfur in this case has 3 electron domains and 2 are bonding. In the oxygen, and now realize there's 2 different oxygens. So one has 4 electron domains and 1 bonding domain, and the other oxygen, this one here, has 3 electron domains and 1 bonding domain. So now if you move on to video 2, you'll be able to put this to practice so you can start predicting the geometry.